Throughout history, humans have been intrigued by certain numbers. Among these numbers, prime numbers have always held a special place. Prime numbers are natural numbers greater than 1 that are only divisible by 1 n itself, and no other number can divide them evenly. Numbers like 2, 3, 5, 7, 11, 13, and 17 are examples of prime because they can only be divided evenly by 1 n themselves. No other numbers can divide them without leaving a remainder. On the other hand, the number 6 is not prime because it can be divided evenly by 1, 2, 3, and 6. It has 4 factors. Therefore, instead of prime, 6 is a composite number. Like all elements made of atoms, all composite numbers can be written as a product of prime factors or a bunch of prime numbers multiplied together. For example, 30 can be factorized as follows. 2 multiplied by 3 multiplied by 5 equals 30. And you can observe that all factors 2, 3, and 5 are prime numbers. Prime numbers are heavily used in cryptography to secure online transactions and communications. In 1977, Ron Rivest, Adi Shamir, and Leonard Adelman at the Massachusetts Institute of Technology used prime numbers to create an algorithm called RSA Algorithm. It is still the most popular cryptographic algorithm for secure data transmission over the Internet. It is an asymmetric encryption algorithm that uses 2 different keys for encryption and decryption. Let's explore how it works. Let's say you want to send a secret message coding. First, we convert this text message to a number by using a number representation scheme like ASCII or any other. But for simplicity, we will keep it the same in text format for our understanding. Next, you take your message and raise it to the power of a special number, which we represent by letter e or exponent, and then reduces the result to modulo n, where n is another special number in addition to e, and it is a product of 2 prime numbers. The result of this formula will give you an encrypted message represented by C, which we call ciphertext. To decrypt a message, you need a set of special numbers, D and N. We will explain how we get these numbers later in the video. In order to extract the secret message from the ciphertext, C is raised to the power of D and then reduces the result modulo N. This will magically equal to the original message. So, in this example, we use the numbers E and N to encrypt, and it is called a public key. The number pair D and N is used to decrypt the message, and it is called the private key. Let's examine one example of RSA encryption and decryption, along with the calculations. First, in order to use the RSA algorithm, we need a public key and a private key. As we discussed earlier, the public is a pair of 2 numbers, E and N, and the private key is a pair of 2 numbers, D and N. Let's generate these numbers so that we can use RSA in action. First, we selected 2 prime numbers, P and Q. We multiplied the 2 prime numbers to calculate N, which is product of P and Q. Next, before we calculate E, we need to calculate a very special number called Euler's totient function of N, which can be calculated by easy formula as shown on the screen. Totient is often denoted by the symbol phi, as shown here. After finding the phi value for N, we will find the value of E, and then finally we will calculate D from the value of E. For our example, I have selected the values of P and Q as follows. P equals 11, and Q equals 13. Next, we multiply P and Q to get N, which in this case will be 11 multiplied by 13, and the result is 143. Next, we calculate the totient function of number N as follows. P minus 1 multiplied by Q minus 1. The result of this will give us a value of totient, which in our case is 120. Now we get to the fun part. In order to calculate the value of E, the value of E is chosen based on the 2 conditions. The first condition is that the number E is greater than 1 and less than the Euler's totient function of N, which is 120. The second condition is E must be coprime to the totient value of 120 in our case. Coprime means E and phi of N must not share a common divisor. Based on the condition, let's start with 3 and see if we can use it as a value of E. 3 satisfied the first condition, it is greater than 1 and less than the totient value of 120. However, it has a common divisor with totient, which is 3 itself. This means we cannot use 3 as a value of E. So, I have selected the number 7 as a value of E for our example. 7 is greater than 1 and less than the Toshan value of 120, and shares no common factor with 120. The last part is to calculate the value of d. The value d is chosen such that when multiplied by e and reduces to modulo of the Euler's Toshan function of n, it must give a remainder of 1. For example, if I choose the number 103 as a value of d, then multiply it by e, which is 7 in our case, and we perform the modulo 120 over the result, it will give us a remainder of 1. So the value of d which we can use in our example is 103. Now, we have all the numbers required for RSA encryption. Let's encrypt a message. Usually, the message is in text format, which we need to convert to a number. For simplicity, let's assume number 83 is our message. As per the RSA formula, we will take the message, which is number 83, and raise it to the power of e, which is 7, and perform modulo n. The value of n is 143. We will get the result number 8, and which is our encrypted message. Now, let's decrypt the encrypted message back to its original value. As per the RSA formula, we will take the ciphertext or encrypted message, which is number 8, and raise it to the power of d, which is 103, and perform modulo n. The value of n is 143. Magically, we will get the original message value of 83. The RSA calculations work correctly. In real-world applications, RSA typically employs a modulus n and a private exponent d, which are very large numbers, often 2048-bit or even 4096-bit integers. Just look at this sample value of n. As you can observe, it's a behemoth of a number, and factoring it to pinpoint the two prime numbers, p and q, that birthed it is no trivial task. These prime numbers are the backbone of RSA, used to compute the Euler's Toshan function, phi of n. This function then plays a pivotal role in determining the value of both e and d. Today, RSA is everywhere, from online banking to the emails you send. RSA is the silent guardian ensuring data transmission remains confidential and secure. And the heart of this encryption marvel? The unique properties of prime numbers. Thanks for watching. Please subscribe to the channel for future videos and updates.